My project seeks to explore properties of the Ising model using stochastic sampling algorithms, compare to analytically derived results, and to explore extensions that have no analytical solution. The Ising model describes a system of interacting spin 1/2 particles, which can take a value of either s equals +1, an upspin, or -1, a downspin. We use a simplified model described by this energy function. We assume that each spin interacts with only its nearest neighbors, the 4 particles to the right, left, above, and below. Neighboring spins aligned in the same direction, or parallel spins, are favored because they have lower energy. The images below are spin configurations of the Ising model at 3 different temperatures. Each colored pixel represents a spin in the up position. It was shown analytically that below a critical temperature of 2.269, the model spontaneously breaks symmetry and nearly all the spins align in the same direction. This is the case in the left image, and it represents the electron spins in a ferromagnet aligning to generate a magnetic field. Above a critical temperature, the system changes phase, and as shown in the right image, the spins over the entire domain average to zero magnetization. We generated these spin configuration samples using 2 algorithms, the Metropolis algorithm and the Wolf algorithm. For numerical simulations, we approximate an infinite lattice by a finite lattice with periodic boundary conditions. The Metropolis algorithm works by updating 1 spin at a time. One iteration consists of the following. Select a random spin and calculate the change in energy that would result from flipping the spin. If the energy decreases or stays the same, flip the spin. Otherwise, flip with probability e to the negative change in energy divided by temperature. This process is repeated once for each spin in the lattice. The figures below show behavior of magnetization, energy, and heat capacity as a function of temperature. Spontaneous magnetization is observed below the critical temperature. Also, for an ideal infinite lattice, the heat capacity, which is the derivative of energy with respect to temperature, diverges at the critical temperature. This is analogous to phase transitions we are used to on a daily basis. When ice melts to water, the energy increases but the temperature stays the same, which translates to infinite heat capacity. One iteration of the Wolf algorithm consists of the following. Select a random cluster seed and examine all neighbors with parallel spins. Add each neighbor to the cluster with a probability that decreases with temperature. This step repeats for all the neighbors of the spins that were just added to the cluster. When the process terminates, all the spins in the cluster are flipped. Whereas in the Metropolis algorithm we saw smoother, more well-behaved energy and heat capacity functions at higher temperatures, here we see better behavior at lower temperatures. This is because only small clusters can form at high temperatures, so exploring the space of spin configurations takes many more iterations. Although the energy function behaves well at low temperatures, the Wolf algorithm is unphysical because there is no longer spontaneous magnetization. We use the same 2 algorithms in the 3-dimensional Ising model, which has no analytical solution for the phase transition temperature. However, the conjecture temperature is plotted and agrees nicely with our simulations. Finally, we apply the Metropolis algorithm to the XY model, an extension of the Ising model. Here spins are unit 2D vectors rather than just plus or minus 1. The energy of interaction between neighboring spins is given by the negative dot product of the 2 spins, so parallel alignment is still favored. Below are images of the spin angles at different temperatures. Although the spins are far more aligned at low temperatures, it has been shown that the average magnetization equals 0 at any temperature. We have learned that certain classes of algorithms work best in different regimes. For example, single spin update and cluster update algorithms work best at different temperatures. Future work includes developing a hybrid algorithm that can efficiently sample at the critical temperature. We also demonstrated that these stochastic sampling algorithms are an effective way to explore models with no analytical solution, such as the 3D Ising or XY models.